Yeah, some morning. So we have two presentations today from students at the center. So the first presentation, both presentations come from the group of Arthur Ismail from chemistry on quantum algorithms. So maybe there are some relations. We will see. You will tell us. So the first one will be by Paarth.
Yes.
Paarth. Paarth. Yeah. He's he's an undergraduate student here at Georgia, before a couple of years already in the group of Arthur. And then the second presentation will be from Praveen. We're having the past from Praveen about your experience in Symmetry. So now it will be about his research and about halfway through the seminar, so within 20 minutes or so, then we switch. There will be time for questions in between and also at the end. So please.
All right, sounds good. Hi everyone, I'm Paarth, an undergrad at UFT, and today I'm going to be presenting on how you could build exact symmetry-preserving quantum circuits. So let's get right to it. Why do we need this? So, as most of you might already know, the oxygen molecule has a triplet ground state configuration, and if you basically want the ground state energy, or you want to build the ground state of wave function of the oxygen molecule on a quantum computer, there are a bunch of ways to do that. One of the ways that people use a near-term way is to use a variational calculation to get the ground state wave function or the ground state energy. Well, the problem with the naive approach or the currently used approach is that when you're trying to do this variational optimization, the optimizer seems to break the symmetries of the molecule. And even though you start with a triplet state, you know that the ground state is also a triplet state. The optimizer kind of collapses onto the singlet, and yeah, the state that you're left with is just unphysical, and you want to do something about it. So before I get into the details of why that happens, for those of you who are not familiar with the variational method, it's a pretty simple, straightforward approach. So the first step is you pick a reference state. So for the oxygen molecule example, you might pick some triplet state. You build a parametrized unitary. So this unitary is basically a product of exponentiated generators. I'm going to get to that part later again. But once you have your parametrized unitary, you use that to measure the energy. And once you have the energy, you're basically just using the energy as, say, a cost function to update your parameters in your unitary. And this is like a hybrid quantum classical loop. You keep doing that until you kind of converge onto the lowest energy possible, and that's your ground state energy. So now that you have a basic understanding of what the variational approach looks like, we can think about the problems in the current approach. Well, the Hamiltonian that you employ here is a normal electronic Hamiltonian, and it has no spin terms, so it commutes with the total spin. So the Hamiltonian is not the problem. The other things that you have in the variational method might be the problem. We'll see about that. So the only thing that you're kind of unsure about is the ansatz. So the VQE ansatz is basically when the parametrized unitary acts on your reference state, and your reference state was also in the triplet configuration, so that should also not be the problem. So the problem lies in the parametrized unitaries that people use. In general, the unitary that people use does not commute with the S squared operator or the total spin. And that's a problem because that basically makes your state drift into the wrong spin sector. And to fix that, you would have to do two things. One, find a unitary that can preserve spin by construction. And the second is you'd have to figure out that, okay, even though you have this unitary, how would you then implement that unitary on a quantum computer that in a way that is not expensive? Well, coming back to the unitary has a bunch of things that you can play around with. The first thing, of course, is the bunch of generators that go into the unitary. So the generators that people employ in the standard case is fermionic single and double excitation operators. And the problem with that is that the double excitation operator does not commute with the total spin. And to fix that, one thing that you would do is take a specific linear combination of these standard generators such that the spin adapted generator that you produce commutes with the total spin. So that's a fix for the first issue. But even though you know that, okay, you can build a generator that would commute with the total spin, the main problem here is how would you then implement the spin adapted generator on a quantum computer? To make the problem in that a bit more clear, we would kind of have to look at what the generator looks like. So in general, the spin adapted generator is a sum of non-commuting operators. And to exponentiate the generator, as in on a quantum computer, you would basically naively employ a trotter-like approach where you can basically split the unitary into a product of smaller unitaries that you know how to implement. So here, you're basically assuming that you know how to implement G1, G2, and so on. And the problem here is how do you implement E of GSA, the spin adapted generator? Oh, right. Oh, I completely forgot that. The pocket. I was hoping that I was loud enough so that the mic picked me anyway, but it's all good. So yeah, the problem is how do you decompose your your large unitary, which is not so straightforward to implement on a quantum computer, into small, solvable, and implementable parts. And like I mentioned, the Trotter splitting approach is not so good for this case because you'd have to use a lot of Trotter steps first, and that's going to increase the depth of your circuits. And you're also going to get an approximation because there is a Trotter error that's going to creep in, and you don't want that to happen. So again, the question that we're left with at this point is how do we rewrite the unitary coming from the spin adapted generators as a finite exact product of single exponentials? Well, the key idea here is that you can take these individual pieces, the operators that you had in the decomposition back there, and you can keep forming commutators in a sense. And surprisingly, this stops. So once you say calculate the commutator of G1 and G2, maybe you get a new operator, you're calling that G3. You're calculating a bunch of commutators of G3 with G1 and G2, so on. You get a lot of operators, and then at the point, you're going to get no new operators. So maybe the commutator of G3 and G4 is going to be G5, and then after that, you find nothing new. So everything is within the set. And this, in simple terms or mathematical terms, is called a closed Lie algebra. And well, this is the structure that we're going to be exploiting to do the decomposition. So here's a small example. And this example is the first thing that we consider in the paper. So you have a spin adapted seniority 2 generator that is built from the two standard spin adapted excitations. And then you look at the commutator of G1 and G2, you get G3. you look at it G1 and G3, you get another operator, you call that G4. You do G2, G3, you get G5. But then after that, when you do, say, G3, G4, or you do G4, G5, then you get G3 again, and stuff like that. So the main point that I'm trying to make here is that you get closure within these 5 operators. Now, how does that make our life easier? Well, it does, because now the first thing that you would do is split the operators in this pool into 2 main parts. One part is very easy to implement, and that's basically the center of the Lie algebra. So the part that commutes with all of the operators in the Lie algebra can be separated out. And because it commutes with all of the other operators, the exponential can be separated, and it would lead to no Trotter error. The second part, which I call the hard part, is stuff that does not form a part of the center, and it has all of the operators that were not, say, a part of the center. So you remove the center from the algebra. What you're left with is called the hard part or the rotation part. So these parts basically just mix among themselves. For this example, they form an SO3 algebra, which is like a 3D rotation algebra, but in general, you could have any rotation part. So like I said, the easy part can be exponentiated individually. The rotation part is the hard one that I'm going to explain how you would do. So there's another trick in here. The trick is that you basically want to write these operators down, the operators in the hard part, as small matrices. In general, if you had matrix representations of each of these operators, the matrices would be pretty huge. You'd have a 64-dimensional Hilbert space, and you wouldn't want to work with such matrices when you do the optimization in the next steps. So the trick here is that you can use the adjoint representation for these operators. Now, what is this adjoint representation and why does it help? The adjoint representation basically gets you a matrix corresponding to each operator. So here in this example, I'm looking at the matrix corresponding to G3. And the matrix is basically trying to capture how one of these operators reshuffles the other operators. And in this example, you can basically see that the commutation of G3 with itself is obviously going to be 0. So the coefficient of G3, G4, and G5 in the right-hand side is 0, 0, and 0. The commutation of G3 and G4 gives you G5. So the coefficients of G3, G4, G5 on the right-hand side are going to be 0, 0, plus 1. And similarly, for the last case, it's going to be 0, -1, 0. And you pack all of these columns into a matrix that I call the adjoint matrix. And this is now an operator that you can kind of replace in the exponential going forward. But the main advantage that you're getting out of this is that now you're working with a 3x3 matrix instead of the 64-dimensional fermionic operators. So now once you've figured out how would you build the adjoint matrices, the problem is really simple. You want a target unitary as a product of simple exponentials on the right-hand side, and you basically would have a bunch of unknown angles to find in this. So you know that you can exactly decompose the target unitary into this product form. And now the important step here is that for each of the operators in the hard part, you're just going to replace the operator by its adjoint matrix. And now, since both of the sides are just going to be small matrices, once you exponentiate them, we can just use a small non-linear fit to find the unknown angles TQs. Once you have the TQs, you basically have the decomposition. And because the size of your matrices, the adjoint matrices, was pretty small, a standard optimization is going to converge really fast. And the factorization that you're going to end up with is going to be exact and you won't have any trotter error in there. So another caveat to this is that when the hard part is also a 3D rotation, like in this example, you don't exactly need an optimization to solve the problem because the standard 3D rotations have this closed form expression for what angles you would end up with. You can just use the Euler angles and get the TQs. So in some of the cases, a very large number of operators in the hard part can just break down into small SO3 subalgebras, and then you can get away without using this nonlinear optimization as well. So we did a lot of math and a lot of different tricks, but did that really help? So here's a check real quick. So we had the black line, which corresponded to the triplet state, and that's what we wanted to reproduce using the VQE algorithm. And the problem was that in the standard method, we would often collapse to the part where the singlet would be produced instead of the triplet. And this is how we're fixing it now. So the red dots basically correspond to the spin adapted generator calculations, and the blue dots correspond to the standard generators. And as you can see, the spin adapted generators solve the problem that we were trying to solve to a very high accuracy. And I guess I already mentioned this, but why does the method work so well? So it has two components to it. First, the size of the numerical fit that you're trying to do using the adjoint matrices is pretty small. And the small matrices just make the optimization problem very small, and you can find these decompositions to like machine precision. And the largest ever adjoint matrix I needed for the examples that we tried out and was just a 24-dimensional adjoint matrix. And that's a very simpler problem to solve as compared to the 256-dimensional quantum space you would have had otherwise in that example. So yeah, that's the key ingredient, the secret sauce. And I guess here's a quick summary of the full pipeline. So the first step is to build your spin adapted generators instead of the standard generators that you would use. The second step is to find closure in the Lie algebra. So you want to make sure that these generators are a part of a small closed Lie algebra. Once you find your algebra closure, then it's pretty simple. You split off the easy part. You can implement the easy part individually as an exponential. And then for the hard part, you can compress the problem down into a smaller matrix using the adjoint representation. The next step is obviously going to be do a nonlinear optimization or solve it exactly if it is the SO3 Lie algebra structure. Once you have these angles, you basically know how to compile each of the G1, G2, and so on into standard gates on a quantum computer. So here's how you would do the whole thing. And the summary is that now you know how to build exact spin preserving circuits, and there's no approximation anywhere in the entire chain of steps. So you basically know that you've done things right. Well, why does this matter? For two main reasons. The first reason is that, well, your variational calculations are going to be better. So you can get better ground state energies, and you can prepare better ground state wave functions using the variational calculations. But if you're excited about the fault tolerant algorithms, such as quantum phase estimation, even in those regimes, you would need to start with a good trial state. And if you do start with a good trial state prepared using the variational calculations, then the cost of the quantum phase estimation is also going to be a lot cheaper. And you will also be preserving the required spin symmetries in this case. Yep. Now that's all from my side. That was the end of that.
Very nice. I can talk question.
Sure. Yeah.
Have you considered trying to do some further algebraic decomposition? Like you said that you get rid of the center because you can implement it like independently from the other things. So have you also considered like taking an irreducible factorization of what's left? Because then you can split it into
Yeah, that's exactly what we do in the paper. So let me go back to this part. So the seniority for intermediate triplet algebra is pretty huge. We have like 128 generators in the algebra to find like complete closure, but then you take the center out and then you have the structure where the algebra can say be decomposed as direct sums or like these products of SO3s, and then you can basically try to find factorizations within those individual algebras. So the problem becomes really small. So for the seniority for intermediate triplet case, I didn't have to do any nonlinear optimization because there was so much structure in the algebra. So yeah, you're right. We do look into those cases. No problem.
What determines the space of the quantum space dimension? Because in principle, you can add more orbitals. So how do you decide on the space?
So the 64 is just coming from 2 to the 6. The 6 is basically just the size of like it's the minimum Hilbert space that you would need in a sense.
So you decide how many orbitals to include. It's already
I'm not sure
stated,
what you
huh?
mean by that.
For the generator definitions,
Yep.
excitations.
Yeah, you have the oxygen 2 problem. In principle, you can add.
Yep.
You decide what's the size of the Hilbert space.
So yeah, go.
Yeah, so essentially the first generator are 4 indices. So to represent this minimally, you need 2 power 4.
2 to the
The
4.
spin adapter needs 6 indices minimally.
Oh,
So you
okay.
need 2 power 6 space to represent this. But if you can, your problem can have more orbitals. But to carry out this decomposition, essentially enough to consider each of these generators separately. So it's a 2 power 6 problem.
Okay, so it doesn't scale with the number of orbitals. It's really the representation for each.
Because it is already factorized into products of spin adaptation. And so then can be treated in the way.
Okay. More
Okay.
questions?
Yep.
Yeah, you can.
Hello. I don't think it's working. It's fine. So yeah, for the step 2 in your final diagram, how much can this decomposition be automated, or do you have to do everything by hand?
This was pretty much automated for me. So you can automate this to the extent that all of the commutator calculations that you need to do can be done using like standard Python libraries. You can use OpenFermion or something like that. One of the collaborators actually has this GitHub where you can find the link to the GitHub in the paper, but he has this library where he does all of these commutator calculations within the library. Yeah.
But do you have to find the original, no, not the closure, but the original operators yourself, the decomposition?
So if I'm getting your question right, you're asking me that
Yes, the G.
do you need to find these guys, the G's, or are you saying do you need to find the spin adapted generators?
I'm not sure, but the one that you use to find the closure.
Aha, right. So you're saying that do you have to manually find G3, G4, all of that?
G1, G2. Yeah.
Yeah, so G1 and G2 were basically the spin adapted generators that I started with. So for the seniority 2 case, you have like 2 spin adapted generators. So they were G1 and G2. So that's basically just defining the problem that you want to solve. And once you've defined, say, the generators that you start with, then you just get all of the commutator calculations, and like G3, G4, all of that, the code is going to calculate for you.
Okay.
Yeah. Yeah. The G3, G4 and stuff like that is mostly just bookkeeping.
So imagine that. So here is it works very effectively for like spin systems, but I want to let's say I want to imagine that I have some like bosonic degrees of freedom that live on an infinite Hilbert space, but there is a lot of like algebra in this. Do you think that there is any like lesson to learn from these methods to effectively represent those variational unitaries where I'm working with bosonic Hilbert spaces, or in general, some infinite Lie algebras?
I'm not sure if I am answering your question by saying this, but I think someone is already trying that out. Like, I think I've read a paper where someone actually tries using something similar to this approach for the bosonic degrees of freedom as well. Are you familiar with that work? No? Okay. Yeah, I can try to find it and share it with you.
Okay, thank you very much. If there is time at the end, we'll have more questions, and then Praveen, it's your.
Right, I put it. I was looking at like large dot bond, so it was not at the equilibrium junction. So the main problem solution there. Yeah, because you tend to fall on to the same.
Okay, yeah, please.
Sure. No.
Hi everyone, I am Praveen. I'm from Arthur's Group, and I'm going to present rough overview of my recent paper with Arthur and Tao Zheng from York University. It's about generally a criterion. We were studying different unitary transformations, and we wanted to understand why they are possible exactly and how efficient such transformations can be. So unitary transformations have been used in many contexts across chemistry, physics, in the chemical physics community for a long time. In general, if you have hard problem and you want to solve for its eigenstate, and you have a black box method, this can be difficult for the black box method. So the general approach is to apply some unitary transformations to make this problem simpler for your black box, and then you solve. Some examples is the interaction picture, where you want to remove your interacting potential between your system and Paarth or something like that. Another approach is just the Heisenberg picture, where you are transforming your operator using some unitary transformations to make your wave function simpler. So in recent years, these kind of approaches have been used in both quantum and quantum-inspired algorithms. For instance, if you look at Qiskit's compiler, like Qiskit's and software stack, there is an option for you if you want to apply a unitary, like what Paarth mentioned, the variational unitaries onto, say, a state. What you can do instead is move a part of the unitary onto the observable being estimated. So the unitary becomes simpler. You have a lesser noise in your system, and hence your calculations can be better. Another approach which has been pioneered by Arthur's group is the quantum-inspired algorithms. For example, the iterative cubic coupled cluster methods, where this has shown to be the benchmark of classical methods. You are essentially transforming the observables, the Hamiltonian, which is being estimated, and you are doing some calculations to get ground state energies. And this method has recently hit around 200 qubits,
It's around 100 molecular orbitals. So these kind of methods have shown a lot of promise nowadays. So a common example which is used in first year courses, grad courses, is the normal modes. If you have, say, bosonic degrees of freedom and you have some bosonic operators, what a normal approach is to convert these operators into normal operators, which are easier to handle with. And this transformation is usually exact for some cases. Another approach is a perturbative approach, which is known as a Schrieffer-Wolff transform. If you have a perturbation potential, you can make it a higher order perturbation by using a particular unitary generator. Notice that in this case, one of them is exact. The other one is not exact sometimes, depending on the operator forms. So one could ask the question, what makes one unitary exact and what makes the other unitaries non-exact? Or is there a possibility to make this exact? So a general unitary transformation is given by an exponential of an anti-Hermitian generator. And the transformation is given by the Campbell identity, or the BCH as it's more commonly known. Where here the commutator is just GH minus HE. So when this infinite summation becomes resummable to finite terms, this unitary transformation is exactly computable. So it is one particular case when this becomes computable. So let's look at this particular case when there's a resummation. So this resummation becomes possible when the commutators close and they form like the higher commutators is equal to the sum of lower commutators. So one could ask, when does such a situation occur? When is this commutator expression closed? Before looking into that, let's ask another question. What about closed Lie algebras like what Paarth talked about? So what if these operators form a closure? What I mean by this is if I take the commutator with G and I acted on a set of operators, say G O1 and O2, the commutator expression results in operators within the same operator set. That is, the operator set O is now closed. So this allows us to write the adjoint representation on this space of operators. And this is generally a linear map which can be exponentiated to give the exact transform. So this can be done when the operator set is closed. So one could check that a commutator closure implies an operator closure just by construction. You can take the nested commutators and these form a closed set. If you take the next commutator of the highest element over here, you're going to get a linear sum of the lower elements because of the closure. So a commutator closure directly implies an operator closure. So does an operator closure imply a commutator closure? Turns out yes. And this is simply a consequence of a Cayley-Hamilton theorem, which basically states that a matrix satisfies its characteristic polynomial. What is a characteristic polynomial? It's given by the determinant of A minus a parameter lambda. So this says that the highest degree of the highest exponent of the matrix can be written as a sum of lower exponentials. So this implies, when you go back to the operator picture, that sum of nested commutators is equal to a lower set. A higher degree commutators is a sum of lower degree commutators. So this implies that a commutator closure implies an operator closure. So we can view a closure or an exact unitary transform in both of these pictures. So is there a benefit from going in one picture versus another? And this is the kind of question I try to answer. Before that, I'd like to pause for any questions. Okay, go and proceed. So an example here is the Heisenberg algebra, which is the XP and the INT operators. Let's take a generator which is given as a linear sum of X and P. So in the space of these operators, the matrix takes this form. And the characteristic polynomial is A cube equal to 0, just because the eigenvalues are 0. And you can take the determinant and you get this expression. But actually, if you check, the second commutator vanishes on any operator in the space when applied onto any operator in the space. So you actually don't need the third power of 8 for closure. So what's happening here where you can find a similarity transform which makes the adjoint transformation into this block diagonal form. And so if the operator which is being transformed is in this first two vector spaces, that is, it's in the span of identity or this operator, you can show that the A square acting on this operator is 0. Similarly, if you take an operator in this third vector span, you can show that the first commutator becomes 0. So the point I'm trying to make here is the knowledge of both the operator which is being transformed and the adjoint representation itself can yield you cheaper transforms. In the case of Lie algebras, it's not a big deal. The Lie algebras are usually small. You can do transforms exactly. So let's look at another example, which we saw recently. So when we began this project, we actually wanted to understand the results of this particular work, where they showed that if I take electronic structure Hamiltonian and I try to transform it by a fermionic excitation, like what Paarth pointed out in his first slides, you can do this transformation repeatedly and get the eigenstates of my Hamiltonian to be more a product state, more simpler state. So if I were to start off with a simple state and do these transformations repeatedly, I can show that the simple state has a lower expectation value, which eventually reaches the ground state energy. So it is useful to transform this operator by this fermionic excitation. Another reason we want to do this transformation with this excitation, this is fermionic number preserving. So it has been shown earlier that this operator has a simple eigenvalue spectrum. It has -1, 0, and 1. So we can use a Taylor expansion and get this Taylor series expansion of the exponential. So this leads to a quartic expression in G. So if I were to compute this classically, I can just use my computer or do a pen and paper calculation to get these expressions. So you need up to 4th power in G. So in this particular paper, what they showed is you can do this same transformation with just 2 commutators with G. So this is just quadratic in the operator G. So what is happening here? Why is this reduction there? This is in a particular case when you're transforming a single fermionic excitation operator. And these fermionic excitation operators are present in the fermionic Hamiltonian which we want to transform. So we wanted to understand why is this closure acting in why is there a closure within like 2 commutators? So for any normal operator G, for example, the anti-Hermitian operators which we use to define our unitary, the projected, by the spectral theorem, you can decompose this into projectors into different eigenspaces. And you can also decompose the transformed operator F into these projected blocks acting between different eigenspaces of my G. So then if you check that, you check the commutator with the G, each of these projected blocks essentially remains invariant with respect to G, only with this constant, which is essentially the eigenvalue difference between the left and the right projectors. So each of these blocks, this is a block representation of this operator being transformed. So each of these entries essentially represents what value you get here. So the adjoint representation over this space of projected blocks is now just a diagonal operator given by diagonal matrix with entries given by these eigenvalue differences. So for an eigenvalue set of -1, 0, 1, the total number of blocks over here is, there are 9 blocks for a 3x3 grid, but this is still not 3. We wanted 2 commutators which needed a vector space of dimension 3. So this is still 9. So there are some reductions and some more scope for improvement. So if you were to group all the projected blocks with the same eigenvalue difference, it would look something like this. So you can group all these blocks with the same differences. For example, these blocks have the same difference -1. These 2 blocks have the same difference +1. So you actually end up with a smaller vector space, which is invariant with respect to the commutator. So you actually have 5 operators, not 9, but it's still not 3. So we are still lacking something. So that particular paper, they showed that there were 2 particular cases, and we were able to show this through this projector decompositions. And we essentially showed that the block structures for these operators being transformed decomposes can be classified into these particular cases. In both of these cases, you only have 3 relevant eigenvalue differences. So the closed set of operators is essentially restricted to 3-dimensional vector space. In our paper, we actually show that there are two more cases in addition to what they showed. So we identified these cases where the closure is essentially two operators. In addition to both of these, which were for the fermionic operators, we show that this is also true for when you are transforming a single polyproduct operator. So why is this useful? In certain, if you recall in my second slide, I talked about the CQIQC operator transformation package. And that essentially works by transforming individual polyproducts in your Hamiltonian. So that process can be made more efficient by using these fermionic operators to transform. And our analysis shows that the whole process is more efficient. So what does this bias? If the original operator being transformed was either a fermionic excitation or a polyproduct, and the generator of the unitary was a fermionic excitation. If I were to do Jordan-Wigner transformation of this fermionic excitation, which is essentially a fermion to qubit space transformation, I end up with 2 power b-1 commuting polyproducts. B over here is the fermionic rank, the number of particles being moved around. So a naive polypropagation, which refers to just propagating each of the polyproduct in the initial Hamiltonian, will give us a scaling of the resulting operators of this form. So essentially, you see that it has a high power, and T here is the number of times you do the transformation. If there was no reductions, we see that there's this scaling. And with our reductions, we show that at most there are this particular scaling. So we get relatively nice scaling. So I'd like to end my talk with some tips on if you want to do this analysis for your operators of interest. So how do you generally find these reductions? You can evaluate these projector blocks directly and determine whether they're vanishing or not. You can, for doing this projection, you can use a general projector. So over here, the generator, if it takes the eigenvalue of interest, it is non-zero. If it takes any other eigenvalue lambda dash, this vanishes. So this projector projects onto the eigenspace of interest. So, but this is not very powerful. It allows you to only project onto a single block. But what really mattered, we saw, is these sums of projector blocks with the same eigenvalue difference. So we'd like to project onto these blocks. So you can use the commutator itself as an operator on the superoperator space, and you can project onto the eigenspace of these commutators. And this will allow you to check or eliminate a lot of blocks at the same time. So both of these operators, both of these projectors are known as Loudon projectors, and these act on the state and operator spaces. Another interesting thing you can do is you can use operator identities. For example, if G and H anti-commute, you can see that if this is 0, whenever the eigenvalue is not the negative of the other, the block should vanish. So if I have a symmetric spectrum like this, you are guaranteed that if G and H anti-commute, you should see a block anti-diagonal structure in your Hamiltonian. So a lot of these blocks vanishes. So the main takeaways from my presentation is that adjoint representation closures make unitary transformations computable. And we've seen that in most known cases, this seems to be the case. We haven't found any other cases. Knowledge of the adjoints, how the adjoints act on a particular transformed operator can simplify transformations. In particular, this makes product transformations cheaper. And this reduction analysis can also be carried on for the operators which Paarth mentioned, the spin-adaptive generators. If you want to do this analysis for operators of your interest, you can look at my code here. I'd like to thank my funding agencies and my supervisor and my collaborators, and thank you for your attention.
Very much. Questions? Are you
So in page 13, I noticed that the first F, the blue blocks are like in diagonal, but in your work, you said you find some F where the blue, like the diagonal, like it
Yeah.
seems disappears. So
Yeah.
can I understand that it's unrelated? How can I see? As long as these colored blocks satisfy some conditions, the diagonal block does not matter.
I think the diagonal block does matter for our purpose. It determines how many non-zero blocks eigenvalue differences matter. In these particular cases, there are specific cases of F which give reductions.
Thank you.
questions? I had a question. It seems like you're suggesting that your work it works for both poly matrices as well as fermionic operators. Is it indeed there are no differences in applying these ideas to? Because obviously the commutation relations are you have it for fermions, but you don't have spins.
The transformations apply for any transformed operator. In the case of fermionic and polyproduct operators, they're simpler. And in particularly, if you retain polyproducts, it's nice because there's no normal ordering to deal with.
Okay.
So the operators don't grow.
Mhm.
It's easier to deal with, like computationally.
Mhm.
So that's the benefit of going to poly.